Hi guys. So before we talk about Euler's formula, I would like to talk about um, the numbers they rely on, because Euler's formula is represented using numbers that most of people are not familiar with, and which were given like the worst name ever. That makes it even harder for neophytes to understand, because they are called complex numbers. Complex numbers, right? I think this should not be called like this because they are not complex. They are not more complex. They are not much more complex than the numbers you are familiar with. And actually, the numbers you are familiar with are a subset of those numbers. And I will show you that those numbers should probably be called 2D numbers, because the numbers you are familiar with, they live on a line, on a one-dimensional universe. They are on a line. You can go backwards with negative numbers, you can go forward, and you can see them as this horizontal line here. Complex numbers, or 2D numbers, are simply living on a plane instead of living on a line. So you can do everything you are familiar with, like 2, usually you would go here. But let's imagine now you can go out of this line. Before you couldn't. But now you can put your point here if you want. So this is your number. This is a different number than this is you, your normal 2 number, and this one is a different one. So how do we identify it? How do we need a way to identify it, because in one dimension all you needed to identify a number was just its value, its name, because you need only one parameter to to identify something on a line. But on a plane you need two parameters, and there are basically two um, equivalent ways to identify a point in space, at least two, and I will show you only those two. I don't know if there are more, but those are the classic ones. So basically, you would say how much you have to go on that line, and then how much you have to go on that line to reach your point. Then you can just draw some arrows that goes there and another arrow that goes there, or you can do it in this order if you prefer, and then there. It doesn't matter as long as you reach your point. The order doesn't matter. But by convention, we write it first the horizontal line, second the orthogonal line. But this is arbitrary. This is a convention. We just all agree on that so that then we don't have to discuss about it. So that's the notation in 2D space. But there is another one. What if I see it as an arrow like this that goes from 0 to my point, and I tell it how much I have to rotate my arrow from the horizontal line pointing right way, like eastward, and what's the length of it. So then if I describe just that arrow that goes from 0 to my point, I just need an angle and the length. And then that gives you also an alternative but equivalent way to describe where to find my point. All right. Yeah, let's just do this. All right, and create a new one. So now I will talk about, well, with normal numbers you can do addition and multiplication. Division and subtraction are just a special case where you are using negative numbers. They are just shortcuts to say multiplying by negative numbers or by a fractional number will give you division, or subtraction. Adding with a negative number is a subtraction. Uh, all I'm saying is that all you need to define is your addition and your multiplication. So with those two, you can derive everything else. So I'll show you how it looks like to add regular numbers like you're familiar with in this space. So your 2, let's say 2 plus 3, right? So your 2 is here. That's an arrow that goes to 2. 3 is here, right? What you do usually, you take that arrow of 3 and you put it after the arrow of 2. You just copy that arrow that goes to 3 and you put it at the end of the arrow that goes to 2. And that gives you where your new point is. So this is 2 plus 3. But in here, it's more exactly 2, 0 plus 3, 0. Because we are 0 on this axis. Okay, let's put another layer. What now if you have a point that is not on the line like we are used to with regular numbers? Let's say I have this point and that point. This one is called 2, 1. This one is called 2, 2. What happens when I add both? I do essentially the same thing. I take that arrow and I put it on top of that arrow. So it will give me this point. So that point plus that point gives me that other point. And all it does is adding arrows together, putting an arrow on top of another arrow. And that gives you a new arrow that goes like this. It's kind of the diagonal of this parallelepiped. I don't know how it's called. But anyway, that's how you add stuff together. Pretty straightforward, right? But now how do we do multiplication? Again, I will talk about how it's done usually on normal numbers. On normal numbers, what you would have is, you can think, usually people think of, let's say 2 times 3. They will think 2 and then multiply 3 times. So they will think of kind of addition where you put that same arrow 3 times on top, right? That will give you 6. Essentially what it does, it multiplied the length of 2 arrows. So it take the arrow of 2 and the arrow of 3 and it multiply the length 2, length 3, and it multiplies them, and that gives you the length of the biggest arrow that goes to 6. Well, In complex space, it is like this too. You multiply the length of the arrow, but you also add the angles. Oops, I think I got a message, but whatever. I wanted to turn them off. Doesn't matter. So, um, you add the angles also. So if we take the same points, let's say here, so we still have 2, 2, and then we have 2, 1. What happens when I multiply them? I will take that angle and add it on top of that already existing angle of the other one, right? So that angle, I'll try to do it as accurate as I can. It looks something like that somehow. So this would go on that line for sure. Would go in that direction, approximately. How far? Well, this is the length of that one, of the first one, times the length of that other one. So it will go probably up to probably here. This is like, I need to compute it, but basically, if it would go approximately there. We don't need to be accurate here. I just want to draw you the um, the feeling, how you should think of multiplication in this space. So it's just multiplying length, adding angles, nothing else. And you can we can do that on Desmos to make sure, like here. But first I need to introduce you how those numbers are written, how complex numbers are written, because here I'm treating them like I want to make sure that it is separated, that this here is a dimension, this here is another dimension, and that's how you should think about it. But the notation that is used nowadays is quite different. It makes it a bit confusing because that same point here, let's keep the arrow, is called 2 plus 2i. This one is called 2 plus I. So basically, they think here there is a I just is a shortcut for 0, 1. So when you write your thing like this, you are essentially saying 2 times 1, 0 plus 2 times 0, 1. That's all you are saying. And I think it's kind of confusing. We should not. So it ends up being 2, 0 plus 0, 2, right? Which is 2, 2. Ah, 2, 2. But I think this is very confusing. So I'm just introducing it here because I didn't want to introduce it first because I think it is confusing. But this you can't avoid because it's all over the place now. It's historical and now it's used everywhere. So including in this tool where I will put the values I said. So P1 equal to 2 plus 2i and P2 equal 2 plus I. And you see essentially it goes 2, 1 and then 2, 2. Nothing more. Now what happens when I put P1 times P2? We said it should be, yeah, you see? So let's take this point here and put it on the other side here. first, let's not show that one. So P, just put a minus here. What do you think will happen? Ah, sorry, that's not what I wanted. Minus here. What do you think will happen here? It will take this angle, and add that on top of that one. So it should go about here, right? And the length should be, I would say it's about here. So now let's show, right? See? It is very simple. There's no complexity about this. I mean, it's actually, ah, it's actually very useful, and we will see why. So now we got the sum and the multiplication. This is all you need to know. Once you know this, you know how to use complex numbers, or 2D numbers, as I prefer to call them. So adding, just put arrows on top of each other. Multiplication, stretch the arrow and rotate it by the sum of the, it adds angle, multiply length, right? So I think this is very useful because, like, you will see a lot of books who will introduce it like this. They would say I square equal minus 1. That's how they will tell you. They will say, or they will tell you it is the solution of this polynomial. Some will even say, and I think this is very wrong, they will say I equal square root of minus 1. This is wrong because then we are mixing. We have to make it clear that we are in a different space. This is true only in a different space, because you need that dimension in order for it to make sense. Outside of real numbers, there is no number that multiplied by itself will give you a negative number. Only in this space you can do that. And why can you do that? Because you rotate. So essentially every time you multiply something by what they call I, but basically on this dimension, if I multiply, that means if I multiply by I, all I do is a rotation by 90 degrees, and since the length is 1, I don't change the length. So all I'm doing is rotating by 90 degrees. So if I take any point and I multiply it by I will get the point that is perpendicular to it. I will get it here, around here. We can check. So here we have like a 2, 1, right? It's already here. This is P2. What happens when I do P2 times I? See? All I did is rotate by 90 degrees. And this is why in this space you can get to minus 1 by squaring a number, because this is on another dimension, and the multiplication is creating a rotation in this space. So I rotate once, 90 degree. I rotate twice, 90 degree. That is I square. And that's why I square equal minus 1. But there is nothing, this is confusing, I believe. I think this is very confusing because when you think about it like a rotation, of 90 degree, then you can make sense of it more. I find it more intuitive. Like for instance, what is the square root of I? Could you tell? What's the square root of I? What does it mean first to be a square root? It means then you multiply, it's the number that when you multiply it by itself will give you I, right? So it's an unknown number that when I square it, it will give you I. That is what square root means. So what point in space here, actually there is two, will give you this? The most obvious one is I is here, right? What number space here will give me I when I multiply it by itself? Well, first, multiplication we said is adding angles. So if we multiply it by itself, that means we double the angle. So it has to be half the angle, half of I. So I is 90 degree, so it has to lie on that line. It has to lie on that line, 45 degree. Because when I do this, if I do any point on that line and I multiply it by itself, it will go on that line, for sure. But now there's another constraint. I is 1 basically. So I need something of length 1. So it has to be about there. And actually, I know that this is 1 over square root of 2. Because the number, because I know that it's at equal distance from the height and the width are the same. And the length is 1. If you use Pythagoras, you know that you have, like, let's call it A. Here it's also A. So you have, Pythagoras would tell you this is this square plus this square plus this square is equal, right? So this is 1 equal is 2a squared. Wait. Isn't that... I got confused. It has to be square root of... Fuck. You have to be square root of 2i squared. And this is equal to square root of 2a. And if you isolate a, that gives you a equal 1 over square root of 2. But doesn't matter because you also know that it is cosine of pi over 4 or sine of pi over 4. And you know also this is very famous, it is 1 over square root of 2. And actually we can check. We can check that the square root of I, you see those two values. First, they are the same. So when I say they are the same, this fits. What's 1 over square root of 2? Right? That's it. Oh, so it makes sense. Here I went for the precise values just to show you that I'm not bullshitting you, but basically I didn't need to compute anything there. I didn't need those things there. Just forget about this. I was able to find the point just thinking about rotation and length. I was like, the square root of I? Well, that's the number. I said there are two numbers, right? Because this one was obvious. It has to be the half, but basically it can also be there, because then you have this angle, and then when you do it again, you would land up back here. So this point is also a valid point. So you have the two solutions are not just 1 over square root of 2. You have another one that is minus. There's one with a minus, basically, the 2 minus. The opposite of this one. But yeah, that's it. Essentially it. And Euler's formula is heavily based on this, basically, on those numbers. It will make sense once you understand those numbers, when you understand how to multiply and add in this space. And that's it.